Category O, Lecture 31, Projective Dimension. Let us start by recalling the classical Category O setup. Let G be a semi-simple finite-dimensional complex Lie algebra with a fixed triangular decomposition into the negative part and minus, the Cartan subalgebra H, and the positive part and plus. We denote by W the Weil group of G, and associated to this decomposition, we have the BG category O and its principal block O0. We know that the category O0 is equivalent to the category of finite-dimensional modules over a certain finite-dimensional associative algebra A. So if we assume that A is basic, then it is defined uniquely up to isomorphism. The algebra A has a number of remarkable properties. So we have seen that this algebra is quasi-hereditary. In particular, it has finite global dimension. And moreover, it is isomorphic to its Ringel dual. The algebra A is isomorphic to its opposite. It is Kosul and even Kosul self-dual. Consequently, the algebra A is isomorphic to the quadratic dual of A. Recall that we have the following structural A modules. They all are indexed by the elements in the Weil group. So we have simple modules LW, we have the indecomposable projective modules PW, we have the indecomposable injective modules IW, we have the Verma modules delta W, these are the standard modules in the quasi-hereditary structure of A. We have the dual Verma modules nabla W, so these are the co-standard modules with respect to the quasi-hereditary structure. And we also have the indecomposable tilting modules TW. So we have the simple preserving duality star on O0, and the dual of the injective module is a projective module. The dual of the Verma module is a dual Verma module, of course, and both simple modules and tilting modules, they are self-dual with respect to this duality. Furthermore, we have the tensor category of projective functors acting on O0, and the indecomposable objects in this category are also naturally indexed by the elements in the Weil group, and we denote the indecomposable projective functor corresponding to W by theta W. It is normalized by the property that theta W sends PE to PW. It also sends IE to IW, and it sends TW0 to TW0 times W. Earlier in the course, we had several formulas describing projective dimensions of some of the structural modules. So consider the standard length function on W, and let W0 denote the longest element in W. So we know that the projective dimension of projective modules is, of course, 0. The projective dimension of the Verma module delta W is L of W. The projective dimension of the simple module LW is equal to 2 times L of W0 and then minus L of W. And the projective dimension of the dual Verma module nabla W is equal to 2 times length of W0 minus L of W. What remains is to find the projective dimension of the indecomposable tilting module TW and the projective dimension of the indecomposable injective module IW. So these two formulas are the main results which will be considered in today's lecture. In order to be able to formulate the answer, we need to recall Lustig's A function. So we have Lustig's A function A, which assigns to an element in W a non-negative integer. One of several possible descriptions of this function is as follows. The value of A on W equals the maximal value of I, for which there exist elements x and y in W, such that if we consider the module theta x LW, it has a non-zero graded homomorphism to Ly shifted by I. So it's a maximal possible degree in which you can have something non-zero if you apply a projective functor to the module Lw concentrated in degree 0. So here are the properties of Lustig's A function, which we already discussed. So this function is constant on two-sided Kazhdan-Lustig cells. The value of this function at the longest element of some parabolic subalgebra equals the length of this element. And in general, the value of this function at any w is less than or equal to the length of w. Note that the first two properties determine the A function uniquely in type A. So this is because any two-sided cell has an element of the form W0P for some parabolic subalgebra P in type A. So here's an example of the values of the A function in the case W is the group S3, which consists of elements E, S, T, ST, TS, and W0. So E is the longest element in the parabolic of length 0, and W0 is the longest element of some parabolic of length 3. Similarly, S and T are longest elements in some parabolic, so the length is 1. And ST and TS, they belong to the same two-sided cell as the elements S and T, so the value of the A function on them is also 1. Now we can formulate the main result of today's lecture. So theorem due to myself from 2007 and 2010. So we have the projective dimension of the indecomposable tilting module TW is equal to A of W. And the projective dimension of the indecomposable injective module IW is equal to 2 times A of W0W. For type A, this theorem is proved in my paper Some Homological Properties of Category O from 2007. And in the general case, it is proved in the paper Some Homological Properties of Category O number 2 from 2010. Today I will present a full proof in type A, and for that proof we will need the following notation. So we denote by T of W the projective dimension of TW, and by I of W the projective dimension of I of W. So let us first look at some special cases. First observation, the claim of the theorem is true if W is the identity element. So the indecomposable tilting module corresponding to the identity element is isomorphic to the indecomposable projective module for W0. So in particular, it is projective, so the projective dimension is 0, which is exactly the value of A at the identity. The indecomposable injective module corresponding to the identity element is just the dominant dual Verma module nabla E. And so the projective dimension of IE is equal, by our formula for the projective dimension of nabla, it is equal to 2 L of W0 minus L of E. So L of E is 0, so this is 2 L of W0. Since W0 is the longest element in the parabolic, this is 2A of W0, and this is of course 2 times A of W0 times E. This shows that the claim of the theorem is true in the case W is the identity element. So the second observation, the claim of the theorem is true if W is the longest element W0. So the tilting module TW0, W0 is the longest element, so this tilting module is simple, and we have a formula for the projective dimension of the simple module. So the projective dimension of the simple module is equal to L of W0, and this is equal to A of W0 because it's the longest element in a parabolic subgroup. So as for the injectives, so IW0 is isomorphic to PW0, so this is a projective injective module, and hence the projective dimension of IW0 is 0, which is equal to 2 times A of E, which is equal to 2 times A of W0 squared. So this shows that our formula works also for W0. So for example, if we consider G to be equal SL2, then W consists only of E and W0, which is S in this situation. So the above special cases exhaust all cases for this type. So the claim of our main theorem is true for SL2. So now let us go to the proof. So the first part of the proof is the following proposition. Both functions t of w and I of w are constant on right Kazhdan-Lusztig cells. Proof. So we prove the claim for t of w and for I of w, the proof is similar. Recall that projective functors are exact and send projective modules to projective modules. Hence, for any module M in O and any projective functor theta, the projective dimension of M is greater than or equal to the projective dimension of theta M. This is because if we take a minimal projective resolution of M and apply theta, we get a projective resolution of theta M. It doesn't have to be minimal, and by exactness it will have the same length. Let's recall also that all tilting modules can be obtained from TW0 applying projective functors. Also recall that the post-composition with theta S, where S runs through the set of all simple reflections, generates the right Kazhdan-Lusztig preorder on W. By combining these observations, we see that the projective dimension must be weakly monotone along the right Kazhdan-Lusztig preorder. In particular, it must be constant on right cells. Next, let us go to left cells. Proposition. Both t of w and I of w are constant on left Kazhdan-Lusztig cells. Again, we will prove the claim for t of w, and for I of w the proof is similar. So we want to adjust the approach used for right cells, but now it will be a little bit more complicated. Recall that the precomposition with theta S, where S runs through the set of all simple reflections, so they generate the left Kazhdan-Lusztig preorder on W. So what we want to prove? We want to prove that the projective dimension of theta W, TW0, is greater than or equal to the projective dimension of theta W applied to theta S, TW0, for any simple reflection S. Well, we know that theta S applied to TW0 is TW0S. And the later module is quite simple. In fact, we have a short exact sequence. So this module TW0S has delta W0S as a submodule and TW0 as a quotient. And the submodule delta W0S can be represented in the following form. If we consider the in-rights completion functor ES, then delta W0S is nothing else but the value of ES at delta W0. Therefore, we can use the following argument. Recall that in-rights completion commutes with projective functors. Therefore, looking at the previous short exact sequence and applying theta W to it, we have the following short exact sequence that ES applied to theta W TW0 is a submodule of theta W TW0S, and then the quotient is theta W TW0. So what we need to prove, so we claim that the projective dimension of the submodule in this short exact sequence is bounded by the projective dimension of the quotient. And then combining these two things together, we will get that the projective dimension of the middle is also bounded by this common bound. So let's prove it. So let's prove the lemma. Recall that the right derived of ES is an equivalence with inverse the left derived of the twisting functor TS. So let L be the direct sum of all simple modules. Then the projective dimension of ES applied to theta W TW0 is by definition the maximal value of I, such that there is a degree I x from this module es theta w tw0 to the module L. Using a junction, we can rewrite this x as x of degree I from theta w tw0 to LTS applied to L, and looking at this x as a home in the derived category from theta w tw0 to LTS applied to L and then shifted by I, we know that LTS moves homology to the left. So therefore, the maximal value of I in such an expression can only decrease. This implies the claim of the lemma, and now looking at the long exact sequence in homology, we obtain that the projective dimension of the middle term is bounded by the projective dimension of the quotient. And this is exactly what we wanted to show. Consequence, both functions t and I are constant on two-sided Kazhdan-Lusztig cells. Proof, we just need to recall that left and right Kazhdan-Lusztig cells together generate two-sided Kazhdan-Lusztig cells. And by the above, we know that t and I are constant on both left and right cells, hence they must be constant on two-sided cells. So in order to prove our main result, what remains is we need to evaluate these two functions at some fixed element of each two-sided cell. And here is an idea in type A. So in what follows, I will present the proof in type A. In type A, we can look at singular blocks. And the special feature in type A is that each two-sided cell contains an element of the form W0 times W0P for some parabolic subalgebra P. And one can connect this element with something in the singular block of category O. So the reason for this is that in type A, two-sided cells are indexed by partitions, and this is given by the Robinson-Shenstedt correspondence. And then for each partition, it is easy to construct a parabolic subalgebra such that the Robinson-Shenstedt correspondent of W0, W0P has the shape of this partition. This is a nice combinatorial exercise. So now let's look at the connection with singular blocks. Fix a parabolic subalgebra P of G containing the Cartan subalgebra H and the positive part n+. Let WP be the corresponding parabolic subgroup of W, and let lambda p be a dominant integral weight with stabilizer WP. Consider the corresponding antidominant weight W0 dot lambda p. Since this is an antidominant weight, the corresponding Verma module is simple and hence coincides with the corresponding tilting module. So we have the projective functor theta p out. So this is a translation from the WP wall. So in our notation for translation functors, it's the functor theta from the dominant weight lambda p to the weight W0p dot 0. So if we apply this functor to our simple standard tilting module LW0 dot p, then the outcome has simple top LW0. In particular, it is indecomposable. On the other hand, it's a projective functor applied to a tilting module, so it's an indecomposable tilting module. And the Verma modules which appear in the Verma flag of this module are exactly the Verma modules delta W0x, where x is an element in the parabolic subgroup. Consequently, so this translated tilting module is exactly the indecomposable tilting module TW0 W0P. Okay, next claim. We claim that the projective dimension of the tilting module TW0 dot lambda p is equal to the projective dimension of the module T W0 W0P. Recall that projective functors are exact and send projectives to projectives. Therefore, applying projective functors cannot increase projective dimension. Since TW0 W0P is the value of a projective functor applied to TW0 dot lambda p, it follows that the projective dimension of this simple singular tilting is greater than or equal to the projective dimension of this regular tilting TW0 W0P. Consider the biadjoint theta P on to our functor theta P out. So in our usual notation, theta P on is the projective functor theta from 0 to lambda P. So what we know is that if you translate out of the wall and then back onto the wall, you will get a direct sum of copies of the identity functor. So theta lambda P is the identity functor on the singular block. And the number of summons is the number of elements in the parabolic subgroup. But this is not very important for us. It's only important that this number is non-zero. But in particular, it follows that if we translate TW0 W0P back to the singular block, we will get a bunch of copies of our simple tilting module TW0.lambda_p. Consequently, the projective dimension of the regular tilting TW0 W0P is greater than or equal to the projective dimension of our simple singular tilting module. So combined together, we have the claim of our lemma. Finally, the claim is that the projective dimension of the simple tilting module in the singular block is equal exactly to the value of the A function at the element W0P, W0. Here, we use the parabolic singular Koszul duality. So the module TW0.lambda_p is a simple module. So the parabolic singular Koszul duality matches the simple module with the dominant parabolic injective module IPE. So this is the dominant injective module in the parabolic category corresponding to P. Recall that the minimal projective resolution of the simple module LW0.lambda_p is linear. In particular, the projective dimension of this module, which is our tilting module, which we want to understand, becomes the graded length of this dominant injective module in the parabolic category. Let D be the Duflo element in the right Kazhdan-Lusztig cell of W0P W0. So we know that the parabolic projective corresponding to D is also injective and is isomorphic to the parabolic tilting module corresponding to E, up to shift of gradient, of course. So therefore, the graded lengths of IPE, which must be the quotient of TPE, coincides with the degree of the maximal non-zero graded component of TPE. Because the socle of IPE is LE, which is in degree 0 here, so the top of IPE will be the maximal non-zero graded component of TPE. But TPE is isomorphic to PPD, and this one is exactly theta D applied to LD. And by the definition of the A function, the maximal non-zero degree for this module is A of D. And since D and W0 PW0 are in the same right cell, then A of D is equal to A of W0 PW0. So now we can complete the computation of projective dimensions of indecomposable tilting modules in type A. So we want to prove that the projective dimension of TW is A of W. Proof? So let us combine the facts which we already established. TW is constant on two-sided Kazhdan-Lusztig cells. Each two-sided cell contains some W0, W0P. This is because we work in type A. And the value of T at the element W0, W0P is equal to the value of A at W0P times W0. At the same time, the conjugation by W0 corresponds to an automorphism of the root system, and hence it doesn't change the value of the A function. So the value of the A function at W0 PW0 is equal to the value of the A function at W0 W0P. And this completes the proof. Of course, we see that outside type A, the same argument gives the result for all two-sided Kazhdan-Lusztig cells, which contains some W0 times W0P. The problem is that not all two-sided cells outside type A have this property. So for other cases, a more delicate argument is necessary, and I refer to my second some homological properties paper for this. Okay, let us now do the computation for injective modules. So we want to prove that the projective dimension of IW is equal to 2 times the value of the A function at the element W0, W. So using exactly the same approach as for tilting modules, the only thing which we need to prove is that the projective dimension of the indecomposable injective IW0P is equal to 2 times the value of the A function at the element W0, W0P. This is because we work in type A. Similarly to tilting modules, we have that the projective dimension of IW0P is equal to the projective dimension of the dominant singular indecomposable injective module I of lambda p. And we claim that the projective dimension of the later module is actually equal to the projective dimension of the dominant simple singular module L lambda p, and this is equal to the global dimension of the singular block, and this is equal to the value of the A function at W0p, W0. Again, we use Kosul duality. So by Kosul duality, the global dimension of the singular block equals the maximal graded lengths of an injective module in the corresponding parabolic block. And we know, of course, that this is achieved on projective injective modules, and we know that all projective injective modules have the same graded lengths. So what we really need, we need to understand the graded lengths of projective injective modules in the parabolic block. But that, we know very well, equals to the value of the A function at the corresponding element W0p, W0. So this gives us the last equality in this formula. So the Kosul dual of the dominant simple singular module is, of course, the anti-dominant injective module in the parabolic block, and the anti-dominant module is, of course, projective. This gives us the formula that the projective dimension of L lambda p is equal to the global dimension of the singular block and is equal to the value of the A function. So it remains to prove the connection with the indecomposable injective. But for the indecomposable injective, we can consider the corresponding short exact sequence. So the simple is the socle of this indecomposable injective, and there is some cokernel. And now we take home into the direct sum of all simples and look at the long exact sequence. So since the projective dimension of the simple module is maximal possible, in the last non-zero term of that short exact sequence, we will have this projective dimension. And so the connecting homomorphism from the X for the indecomposable injective module must be surjective. So this is because the projective dimension of L lambda p is maximal possible, and after that term in the long exact sequence, we must have only zeros. So this implies exactly that the projective dimension of this indecomposable injective module is also maximal possible. That is given by the A function. So this completes the proof of the main theorem. Let us look at the Sl3 example. In the case of Sl3, we have the W consists of E, S, T, ST, TS, and W0. So the projective dimension of TE is 0 by projectivity. So the projective dimension of TW0 is 3 because TW0 is the corresponding delta, STS, which is a simple module, and the length of STS is 3. So the remaining cases ST, ST, and TS form a two-sided cell of A value 1. We have that the standard filtration of TST consists of delta ST as a submodule and delta W0 as a quotient. So using this, it is easy to see that the projective resolution of TST has the following form. So TST is covered by PW0. This is because the quotient is delta W0. And then if you take from PW0 these two standard modules in the standard filtration, what remains forms the indecomposable projective PTS. So this shows that the projective dimension of TST is indeed 1. Similarly, for the tilting module TT, the standard modules which constitute its standard filtration are delta T, delta TS, delta ST, and delta W0. And now the minimal projective resolution of TT, again, TT has a stop delta W0, so it is covered by PW0. And if you take away these deltas from the standard filtration of PW0, what remains is PS. So this also shows that TT has projective dimension 1, projective resolution with two projective modules. Okay, as a bonus for today's lecture, let us also compute projective dimension of twisted Verma modules. So for W in W, we have the corresponding twisting functor TW, and we have defined the twisted Verma modules Tx applied to delta W for x and y elements in W. Alternatively, the same family of modules can be described using the shuffling functor CW, where W in W. So the family of modules of the form Tx applied to delta y is equal to the family of the modules of the form Cx applied to delta y. But note that each component here is equal to the corresponding component here. So this is equality of sets. Theorem from my first some homological properties paper. For x and y in W, the projective dimension of the corresponding twisted Verma module Tx delta y is equal to L of x plus L of y. Some special cases. If x is the identity, we have the corresponding Verma module delta y, whose projective dimension we know to be equal L of y. And if y is equal to W0, then Tx applied to delta W0 is a dual Verma module nabla x times W0, and that one has a projective dimension L of W0 plus L of x. Okay, so to prove the formula for this projective dimension, let us first establish an upper bound. So we claim that the projective dimension of Tx delta y is at most L of x plus L of y. We prove this by induction on L of x. So if L of x is equal to 0, then delta y is a Verma module, and we already know that its projective dimension is equal to L of y. So that's fine. For the induction step, let S be a simple reflection such that Sx is greater than x. Then we can write Tsx as Ts after Tx. So we know that Ts is acyclic on Tx delta y. Therefore, using a junction, we can write that home in the derived category from LTS applied to Tx delta y to L with arbitrary shift I in homological position is equal to the home from Tx delta y to the right derived of the Enright's completion functor Es applied to L with the same shift in homological position. So there are shifts missing in this formula. And we also know that the right deriveds of the Enright's completion Es are 0 for all degrees that are greater than 1. From this, it follows that the projective dimension of Tsx delta y is bounded by the projective dimension of Tx delta y plus 1. And this establishes the induction step. Okay, let us derive a lower bound. So we claim that the x of degree L of x plus L of y from Tx delta y to Le is one-dimensional. Again, we do induction on L of x. We know that Verma modules have linear minimal projective resolutions, and we know that for the Verma module delta y, the corresponding minimal linear projective resolution is a costandard object nabla Y inverse W0 in the category of linear complexes of projective modules. So this costandard object has simple top LW0 in degree minus L of Y. And in the category of linear complexes, this is realized as PE at the homological position minus L of Y. And this exactly proves the basis of the induction, because this PE gives us a one-dimensional X to LE. For the induction step, let S be a simple reflection such that Sx is greater than X. And then we can do the following computation. So the X of degree L of Sx plus L of Y from Tsx delta Y to Le can be written as a derived home from Tsx delta Y to Le shifted by L of Sx plus L of Y. Again, we rewrite Tsx as the left derived of Ts applied to Tx, and move the left derived of Ts by a junction to the right. So we will have here the right derived of the Enright's completion Es. And now we have here the right derived of the Enright's completion applied to the dominant simple module. So this just shifts this dominant simple module one step to the right. And this exactly corresponds to the deletion of this simple reflection S in the lengths of Sx. So we shift it to the right and we delete this X, and we get the derived home from Tx delta Y to Le shifted by Lx plus L of Y. And this completes the proof of the lemma, and hence completes the proof of our formula for the projective dimension of twisted Verma modules. Here is an Sl3 example. Again, we have Sl3, and the while group is E, S, T, ST, TS, and W0. So the graded Löwe filtration of the S-twisted Verma module delta S, which by the way is isomorphic to the S-shuffled Verma module delta S, looks as follows. We have S on top, and then the next layer is ST, TS, and E, and then we have the socle consisting of W0 and T. So the projective resolution of delta S looks as follows. So delta S is covered by PS, with the kernel being PE shifted by -1. So in particular, we see that this is a linear resolution. And now for the corresponding shuffling, so if we now shuffle and look at CS times delta S, so we should apply theta S to this resolution, and then take a home from delta S to each and do the cone. And then we will have a cancellation of PS of one PS coming here and one PS coming here. And in the outcome, we will have that the projective resolution of CS delta S looks as follows. So this module is covered by PS because S is a simple top here. And then the kernel of this map is exactly delta S. So it is covered by PS shifted by -2 because S here will live in degree 2. And then the next kernel is exactly PE shifted by -3. So the projective dimension of CS delta S is equal to 2. Finally, some questions for PhD students. Question number 1. Compute all minimal projective resolutions of indecomposable tilting modules in the regular block of O for Sl3. Question 2. Compute all minimal projective resolutions of the indecomposable injective modules in the regular block of O for Sl3. Question 3. Compute all minimal projective resolutions for indecomposable tilting modules in singular integral blocks of category O for Sl3. Question 4. Compute all minimal projective resolutions of indecomposable injective modules in all singular integral blocks of O for Sl3. And question 5. Compute the minimal projective resolutions for all twisted Verma modules in the regular block of category O for Sl3. Thank you very much, and see you next time.